Welcome to The Explainer. You know, that very first chapter of physics, units and measurements, can often feel, well, incredibly dry and frankly a bit intimidating. But today, we're completely transforming it. Think of this as building your foundational toolkit. We're going to take those massive, overwhelming concepts and break them down into simple, highly logical tools that you can actually use to decode the physical world. Sound good? Let's get right into it.
So, let me ask you something right off the bat. Can you measure your feelings? Like, say, your feelings for your current crush? You might joke that they're infinite, or, well, perhaps the feelings they have for you are exactly zero. But scientifically speaking, no way. You absolutely can't measure them. And in physics, it's pretty strict. If we can't measure it, it is simply not a physical quantity.
Okay, so what actually can be measured? Well, a physical quantity is basically any property of a material or a system that you can put a definitive measurement on. For instance, if I tell you my weight is 70 kilograms, boom, I've just given you a physical quantity. And notice how it's broken down into two absolutely crucial components. You've got a numerical value, the 70, and a unit, the kilograms. Every single physical quantity you'll ever encounter relies on this exact partnership between a number and a unit.
Now, I know this topic can seem huge, but don't worry, we've got a roadmap. We're going to conquer this in 5 totally logical, manageable steps. First, the language of physics. Second, decoding dimensional formulas. Third, the principle of homogeneity. Fourth, actually deriving physics formulas. And finally, mastering significant figures. Okay, let's dive into this. Section 1, the language of physics, building the foundation. Just like learning any new language requires an alphabet, physics requires basic units. And there are really just two main types. First, we have fundamental units. These are basic, independent units that we just accept as the absolute standard, kind of like the primary colors of physics. Then we have derived units. These are the units we construct by multiplying or dividing those fundamental units. Because think about it, you can't measure something like area or velocity with just one fundamental unit, right? You actually have to derive them by combining lengths and times. So here are the 7 fundamental units of the MKS or SI system. Honestly, you probably recognize a lot of these from your 10th grade science classes. We've got the kilogram for mass, the meter for length, and the second for time, plus the ampere for current, Kelvin for temperature, mole for the amount of a substance, and candela for luminous intensity. These 7 standard units are accepted worldwide. They're what allows scientists all over the globe to communicate consistently without a hint of confusion. But hey, sometimes we need to change how we express these units, right? Which brings us to the conversion rule. N1U1 equals N2U2. The N just stands for the numerical value, and the U is the unit. The absolutely crucial concept to grasp here is that the numerical value is inversely proportional to the unit size, meaning as your unit gets smaller, like going from meters down to centimeters, your numerical value literally has to get bigger to keep the physical quantity exactly the same. Let's move to and see how this builds into a real example. Say we're converting 3 meters into centimeters. Super simple. Step 1, we identify our parts. N1 is 3, U1 is meters, and U2 is centimeters. Step 2, we set up our equation. We already know 1 meter equals 100 centimeters, so we just plug that in. 3 times 100 centimeters equals our unknown N2 times centimeters. The units naturally cancel out, and step 3 gives us our answer. N2 equals 300. So 3 meters is 300 centimeters. See, the unit got smaller, so the number had to get bigger. Section 2, decoding dimensional formulas, writing the words. All right, now that we have our fundamental alphabet down, it's time to start writing some words. M to the power of 1, L to the power of 1, T to the power of -2. Listen, if you remember only one single dimensional formula for your exams, make it this one. This is the dimensional formula for force. Force is just mass times acceleration, which is kilograms times meters per second squared. Translated into dimensions, that is M for mass, L for meters, and T-2 for the second squared sitting in the denominator. Write it down because this is your ultimate cheat code. And this brilliantly illustrates exactly why force is a cheat code. Knowing just that one formula instantly unlocks a whole bunch of others. Need the dimension for work or energy? Well, work is just force times length. So you literally just take the force dimension and tack on another L, giving you M1, L2, T-2. Need pressure or stress? That's force divided by area. So you just divide by L squared, leaving you with M1, L-1, T-2. Memorize force and you've got the key to the rest of the whole shebang. Moving on to Section 3, the principle of homogeneity, constructing valid sentences. So,
We have written our words, and now we need to construct valid sentences. In physics, equations have really strict grammar rules, meaning only compatible terms can interact with one another. Let me pose this somewhat absurd question to you. Can you add 10 kilograms and 10 centimeters? Of course not. It's mathematically and physically impossible. You can't just add mass to length. You can only add or subtract values that share the exact same units.
And that brings us right to the formal definition. The principle of homogeneity states that an equation is dimensionally correct only if the dimensions of each term on both sides are identically the same. Think about that classic kinematic equation you know, final velocity equals initial velocity plus acceleration times time, or v equals u plus at. For this equation to actually be valid, v, u, and that combined term at must all have the exact same dimension, which is Lt-1.
Section 4. Deriving physics formulas, the power of dimensions.
And now we are getting to the most advanced and empowering tool in your entire toolkit. We aren't just checking existing formulas anymore. We're actually using dimensional analysis to discover and derive brand new formulas from scratch. Let's break down this seemingly terrifying algebra into 3 foolproof steps. Suppose we want to find the formula for the time period of a simple pendulum. Step 1. We know it depends on length, L, and gravity, G, but we don't know the exact powers. So we just assume proportionalities. Time period T is proportional to length to the power of X and gravity to the power of Y. Step 2. We write out the dimensions. T equals L to the power of X multiplied by gravity's dimension, Lt-2, all to the power of Y. Step 3. By matching the powers of L and T on both sides, we solve some simple algebra to find that X equals positive 1/2 and Y equals negative 1/2. So when we plug those powers back in, the power of a half becomes a square root, and that negative power, it drops the gravity right into the denominator. And we arrive at this beautifully simple final formula. T equals a constant K times the square root of L over G. Look at that. Just by knowing the basic dimensions, you logically deduce the actual physics formula for a swinging pendulum. How cool is that?
And finally, Section 5, Mastering Significant Figures, Speaking with Precision. We have officially reached our final stop. Here, we're shifting our focus away from units and formulas and looking at the precision of the numbers themselves. When a physicist measures something, they need to communicate exactly how precise that measurement really is. Let's concisely summarize the strict rules for identifying which digits actually matter. First off, all non-zero digits count. Always. Second, zeros trapped between non-zeros count. They're sandwiched in there, so they matter. Third, leading zeros at the very front of a number, they never count. They are purely placeholders. Fourth, trailing zeros at the end of a number only count if there's a decimal point present. And finally, exact numbers, like saying there are exactly 11 students in the room. Those have infinite significant figures because there is absolute zero uncertainty in that count. Now, what's really interesting about this slide is the rounding rules, specifically when a number ends exactly in 5. So if the last digit is less than 5, you just drop it. Easy. If it's greater than 5, you add 1 to the previous digit. Also easy. But if it ends in exactly 5, there's a special odd/even rule you gotta follow. You only add 1 if the previous digit is odd. For example, take 4.635. Because that 3 is odd, we round the whole thing up to 4.64. But actually, if it had been an even number, we would have just left it alone. So what does this all mean? We've covered the language of units, the dimensional cheat codes, equation grammar, deriving formulas from scratch, and even the precision of numbers. But before we wrap up today, I want to leave you with a bit of a challenge from the source material to really apply your new physicist toolkit. Based on everything we discussed today, what are the dimensions of centripetal force? As a hint, the formula is F equals m times v squared divided by r. Seriously, grab a pen, write out the dimensions for mass, velocity squared, and radius, and see if you arrive right back at our ultimate cheat code. Thanks for exploring this with the explainer today, and keep questioning the physical world around you.